This is an AI dialogue, a quiet colloquy, meant to be listened to rather than watched. Closed captions available.
What are 3 or 4 major and fundamental design features found in most cars today that would have seemed like astonishing genius to automotive designers 100 years ago?
That's a great question, because if you dropped a modern, completely ordinary car into the year 1926, even the most brilliant automotive engineers of the time would be genuinely stunned. Not because the basic ideas were unimaginable, but because the level of integration would have been far beyond what their materials, tools, and ways of thinking could support. One of the most shocking features would be the idea of crumple zones. Early automotive designers believed that stronger meant safer, so frames were rigid, heavy, and unforgiving. The modern concept that a car should be designed to sacrifice itself in a crash, deforming in carefully engineered ways to protect the occupants, would have felt almost backwards. What's remarkable isn't simply that metal bends, but that engineers can predict how energy will move through a structure, tune how fast different sections deform, and preserve a rigid survival space for passengers. All of that happens passively, without sensors or moving parts. To someone in the 1920s, this represents a deep shift from thinking in terms of strength to thinking in terms of energy management. Anti-lock braking systems would have been equally disorienting. The early intuition about braking was simple. More braking force should mean a shorter stop. Anti-lock braking systems violate that intuition by repeatedly releasing brake pressure many times per second to maintain traction. The genius lies in recognizing that wheels don't actually stop cars, tires interacting with the road do. That insight depends on understanding friction curves, slip ratios, and feedback loops, none of which could be practically implemented a century ago. Even if the concept could be imagined, the execution would have seemed like magic. Electronic engine management would have felt revolutionary rather than incremental. A modern engine constantly adjusts fuel delivery and ignition timing, compensates for altitude and temperature, adapts to wear and fuel quality, manages emissions, and even diagnoses its own faults. In the 1920s, engines relied on purely mechanical carburetors and often manual, hand-operated ignition timing, and they ran rich, simply to survive variation. The starting part isn't the presence of electronics, but the existence of closed-loop control systems that continuously sense, compute, act, and correct. To an early engineer, an engine that adapts itself would have seemed almost alive. Electronic stability control might have felt the most uncanny of all. These systems don't wait for a crash to occur. They anticipate loss of control by comparing the driver's intended motion with the vehicle's actual motion, then selectively brake individual wheels and reduce engine power in milliseconds. The machine intervenes before the driver is even aware that something is wrong. 100 years ago, the driver was assumed to be the smartest system in the car, and the idea that a machine could preemptively correct a human would likely have felt absurd, even offensive. Yet today it quietly prevents accidents every day. What unites all of these features is a single, counterintuitive insight. The car is no longer a passive machine that simply obeys mechanical inputs. It is an active system that senses, interprets, decides, and intervenes, usually subtly, and often invisibly. That shift from mechanism to system is the real revolution. If you told a 1920s engineer that cars would intentionally crumple, momentarily release brakes to stop faster, think about combustion thousands of times per minute, and correct steering errors before the driver noticed them, he wouldn't argue the benefits. He would ask how any of this could possibly be made reliable. And that question is where the last century of engineering genius truly lives.
A friend of mine is an auto mechanic with a small shop in a rural town, and he works on all makes and models. It's often occurred to me how mind-numbingly complex that work is. It could be any year, any make, any model, any problem. Modern vehicles are so complicated, that it seems like a huge challenge. If you took a top auto mechanic from 1926 and put him in my friend's shop and told him to go to work, I suspect there'd be very little he could do.
You're almost certainly right, and not because that 1926 mechanic would be unintelligent or unskilled. He would be disoriented at a categorical level, much like a master blacksmith dropped into a semiconductor fabrication plant. What would stop him isn't difficulty, but the fact that the nature of the work itself has changed. A top mechanic in 1926 had extraordinary strengths. He possessed deep tactile intuition, a strong sense of mechanical causality, and an ability to diagnose problems using sound, smell, vibration, and feel. Those skills were perfectly matched to machines that were mechanically transparent and causally linear. Modern vehicles violate all of those assumptions. In 1926, when something failed, the failure usually occurred where the symptom appeared. It was often visible, audible, or tangible, and diagnosis and repair were nearly the same act. In a modern shop, the symptom may be far removed from the cause. The cause may be digital rather than mechanical, and the vehicle may even be masking the underlying issue as a form of self-protection. Your friend doesn't begin by listening to the car. He interrogates it. That alone would feel alien. The second shock would be abstraction. A 1926 mechanic lived in a world where force led to motion led to wear, and wear led to failure. A modern mechanic works in a world of signals, interpretations, decisions, and actuations. A failing throttle might not be a cable or a linkage at all, but a disagreement between senses, a drifting voltage reference, or a software veto. Nothing is broken in the classical sense. The system has simply decided not to cooperate. To someone trained in mechanical inevitability, this feels almost dishonest. The third shock would be the role of tools. In 1926, skill lived primarily in the hands, and tools merely amplified that skill. Today, the scan tool is the first diagnostic organ. Access to software determines what can even be seen, and repair often means persuading a system to accept a change. When the 1926 mechanic asks where the problem is, the honest answer may be that it exists in a state table he cannot see. That isn't a small adjustment. It's a different way of understanding reality. What's remarkable is not that the old mechanic would struggle, but that your friend succeeds. He isn't just fixing cars, he's translating between eras. He moves between dozens of incompatible design philosophies, holding multiple mental models at once. Each vehicle brings its own electrical architecture, sensor logic, failure priorities, and proprietary quirks. There is no single car anymore, only individual expressions of design intent. That's why rural generalist mechanics are quietly heroic. They do the work specialization was supposed to make unnecessary. The irony is subtle but sharp. The machine is now smarter, but the human must work harder to understand it. Progress didn't eliminate complexity, it relocated it, from metal to logic, from wear to disagreement, from repair to reconciliation. Your friend isn't restoring function so much as restoring coherence. A 1926 mechanic wouldn't be obsolete. He would be illiterate in a new language. Unliteracy, not intelligence, is the barrier. If that mechanic were truly great, he would sit down, watch, learn, and adapt. Because mastery isn't about what you know, it's about whether you can cross paradigms without resentment. Your friend does that every day, often without anyone noticing how extraordinary it really is.
What happens if we flip the question and ask what hasn't improved as much as expected? How do cars compare to tractors or aircraft? And which modern systems turn out to be fragile illusions?
Those angles reveal why modern cars can feel simultaneously miraculous and oddly disappointing, depending on where you look. Some things have improved far less than engineers in the 1920s might have expected. Mechanical longevity is a quiet example. Engines today are cleaner, more efficient, and more powerful per litre, but they are not proportionally longer lived relative to their complexity. A century ago, one might assume that precise fueling and electronic control would lead to near indefinite life. Instead, tighter tolerances, multiplied systems, and economic service life targets have increased sensitivity to neglect and contamination. Modern engines are brilliantly optimized, but far less forgiving. Serviceability and intelligibility have also declined. Early cars were crude, but legible. Modern cars hide function behind abstraction, replacing understanding with diagnostics and requiring software mediation, even for simple faults. Nothing here violates engineering logic, but it does violate mechanical common sense. This isn't progress or regression so much as a shift in who the machine is designed for. Human-machine harmony is another area where improvement has lagged. Cars now protect drivers from physics, correct their errors, and anticipate failure, but they haven't made people better drivers or reduced cognitive overload. In many cases, driver skill has declined as system dependency increased. The machine improved faster than the human. Comparing cars to tractors and aircraft makes the reason clearer. Cars evolved under mass consumer demand, regulation, and marketing pressure, leading to extraordinary integration but fragile complexity at the edges. Tractors evolved under durability and owner maintenance constraints, favoring simplicity and mechanical honesty. Aircraft evolved under failure intolerance, prioritizing predictability and graceful degradation over novelty. All three use similar technologies, but progress followed the tightest constraint. As for fragile illusions, modern reliability often depends on software masking faults, rerouting around degradation, and warning only after systems are already complex. These machines are safer until they aren't, and when they fail, they often fail opaquely. Old machines degraded linearly. Modern ones sometimes fail catastrophically. Redundancy can also delay human awareness and encourage overconfidence, leaving operators less prepared when multiple systems fail together. The unifying insight is that we stopped building machines that teach their users how they work. Older machines demanded attention and trained intuition. Modern machines absorb mistakes silently and externalize understanding to specialists. That isn't evil, but it changes the relationship. Modern cars are marvels, but they are marvels of orchestration rather than robustness.